Okay. Thank you, my colleagues. We solved this problem successfully. It's a great success. Now I can change the slides. And let me present you the next slide. It's top decay properties within the standard model. As I told you, the top quark gives its huge value of the VTB, which equals to 1. The main decaying channel, in fact, within the standard model is a dominant decay channel. The branching ratio is about 99.99%. It's the top decay into B quark and W, and therefore all decay channels and properties of the top to the different decay channels are predicted by the W decay branching ratio. The expression of the total top decay widths are presented here with linear order corrections, and if you take into account the quantity and use the maybe more or less the correct value of the experimental value of the top mass, the total decay width is about 1.39 GeV. And let me remind you that it's about 2 times or even 1 order of magnitude bigger than the lambda QCD. As a result, this is why we don't expect the existence of the top hadrons. So we have top quark. I mean, we can produce top quark. What we can expect in the final state? The final state, in this case, also for TT-bar pair production is very trivial. We have at least 2 big quark in any final state. We have, if we consider that both top decay hadronically, we expect six jets in the final state. The branching ratio is about 50%. Maybe on the clean the decay channel, when the top TT-bar pair decays of BB bar and the 2 charged leptons. Sorry for this, please. However, the branching ratio is not very huge, about 10%. Therefore, if we wish to reconstruct the top quark, we need first reconstruct the hadronic jets, and moreover, we should also distinguish the usual jets from the bit jets. So we need to use a so-called bit tagging procedure. This is typical picture for top quark reconstruction. In the left side, you see the top decays into B jet W, which also decays to charged lepton pairs, and some irradiation of maybe produce light jets due to irradiation for the top production processes, and the pure hadronic case when the W decays to light quarks. And this is explanation why, if we wish to reconstruct or measure top quark mass or the quark width, we cannot use traditional methods. Let me remind you that we cannot reconstruct explicitly the momentum of the B quark. We can reconstruct B jet momentum. Then we need to use some specific tricks to recalculate the reconstructed value to the initial quark for momentum energy or for momentum energy and free momentum, but this during a reconstruction procedure we obtain some additional error. And typical picture which show you the distribution of the invariant mass of the 2 light jets is presented here, is the W. So we see more or less peak within the mass of the W, but the width is very, very huge. And the same picture we should expect, and we've seen it if we try to reconstruct directly the mass of the top. So the naive expectation, if we use the definition of the width on the 1/2 of the highway, it's about several tenths of the GeV. Therefore, we cannot use the traditional way to reconstruct of the top. Once again, we have a problem. Sorry. Yes. окей? Не знаю, посмотрим. Не окей. So as I told you in the beginning, the theoretical predictions concerning the top quark mass is very high, it's about 1%. And here you can see the latest results, which summarize the measurements of the top quark, or more precisely TT bar production cross section. Here is the data from the Tevatron, and the blue curve, it's prediction for the PP bar collisions. The green curve represents the predictions for the PP collisions, and you can see we have at least, let me remember, 7 points of the TT, which corresponds to the total cross section TT bar production, different energy. Here, with the most accurate measurements of TT bar pairs at the square root of about 13 GeV, you can compare the theoretical measurements with the experimental data with theoretical predictions, and you can see that the agreement with the QCD prediction is very, from my point of view, excellent agreement. And this year it was appeared two values with the highest energy, the 13.6 TeV, the around free data, and the experimental value slightly lower than theoretical predictions, but anyway, it's the first measurements, the statistics is not very large, so we did not consider this discrepancy, or even this discrepancy, maybe some first results, so we certainly expect that as a future measurement, when we can increase the total luminosity, the agreement will be better. And in this slide, you can see the comparison of the experimental results with theoretical predictions. And let me remind you, when we calculate the theoretical these values, now the main uncertainty come from the PDF. Sorry. Now from the PDF. These three lines present you the latest results for this value of square root of S. You can see that the total luminosity about for the CMS of 1.21 inverse femtobarns, the Atlas had obtained bigger luminosity. Let me remind you, the total luminosity explored at the square root of 13 GeV is about 100. This presents the value, the measured cross-section value is from one point of view, more or less compare with these experimental results. And here you see the theoretical predictions. That's why sorry. Не могу переключить. That's why I show you, we concentrate on this point where the theoretical experimental measurements are smaller than theoretical predictions. For the recently, for maybe during the last 3 years, it was appeared several interesting measurement. Maybe the most interesting is the 4 top quark production. 4 top, it means 2 top quarks and 2 T-bar quarks. First of all, there are 2 reasons. The first of all is this process is one of the most rarest process which can be measured at LHC. The cross section is about 4 orders of magnitude smaller than TT bar production. Another interesting is that the explicit measurements of this process provide us to independent way to measure the Yukawa coupling constants. There are both experiments, I mean the Atlas and CMS has measured these processes. At present, the CMS has slightly better uncertainties, but in near future we can certainly all these experiments will predict here. There are also measurements of TT bar production with W and Z. This is very interesting very important results, because here we can measure measure explicitly in geophysics. And sorry, there is no window to show you these results. The first measurements, which is provided by Atlas experiments, the Yukawa coupling of the Higgs with TT bar is more or less with agreement with the standard model predictions. There are also two interesting results. First, CMS plus totem collaboration. Let me remind you that totem is special detector which situated very far from the CMS detectors and provide us to measure the final two protons. In fact, we can study the exclusive processes. And they obtain first results of the measurements of these explicitly final state. There are no acts in the final state. So they measure the processes when you have in the final stage 4 particles, 2 protons and TT bar pairs. There are 2 processes from theoretical point of view which can produce these reactions. The first one is the usual gamma-gamma interactions, which certainly with a small value of the cross-section. But maybe the most interesting is so-called 2 Pomeroy interactions. Since at present we don't know explicitly what does it mean Pomeroy, we believe that it's multi-gluon exchange, but who knows? So the measurement of the process provides us additional way to investigate the Pomeroy structure. And since the top quark has very, very nice, we can predict the TT bar production with very high accuracy. Therefore, this is also a very good way to investigate the Pomeroy structure. The cross sections is more or less within theoretical expectation. Maybe another interesting observation. You know that during this workshop we have heard several talks concerning the nucleus interactions, and CMS provides the first measurements of beta states, evidence for the top quark production in nucleus interactions. This square root of S related to nucleons is about 5.5 TeV, and there are also measurements of the CMS as a small energy in PP collisions. And if we recalculate the measurement cross section, which is measured for the PP collision at the same square root, we'll obtain more or less the recalculated cross section is more or less coincides with the CMS results, but this difference about 2 times. But look, the errors is too big that we consider the differences in some sense more or less serious discrepancy. But at present there is some contradiction between 2 results if we recalculate this value to use the A squared recommendation. Well, let me present you maybe just only explanations, few results concerning the measurement of the top quark mass. This is an interesting question. Why? Because strictly speaking, nobody knows what we are measured in the experiment. There, as you know, there are several definitions of top quark. It's pole mass or mass of the top, and blah, 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 blah. But our experimental colleagues ask us, how we can call these quantities that we can measure in the experiment. So our moral general recommendation, let us call it pole mass. There are several ways to measure this quantity within the experiment. The first one, we can use a reconstruct of the B-jet and the reconstructed W. Another, but this is very, very bad precision. Another way, we can use so-called transverse mass of the charged lepton and missing ET, and also we can use the invariant mass of the lepton, and maybe the latest way is to measure cross-section production, which should be strongly dependent on the mass of the top. They combine all these measurements. In fact, there are 15 measurements. The final results are presented here. The mass of the top 172.25. Plus, look at this arrow. It's extreme very, very interesting result. The error is less than several tenths of the percent. The final value which you can find in the RPP issue particle data group, the error is compatible. Its picture provides you the different measurements of the top quark mass. And maybe let me spend a few minutes concerning the explanation how we can measure the total top decay width. Certainly we cannot measure this value by using traditional way. But the Atlas explores the following trick. They calculate different, they use different distributions like PT spectrum, invariant spectrum of the lepton, blah, 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 and perform the Monte Carlo predictions with, and they use a scan of the top mass starting from 0.1 GeV up to 5 GeV. And using the minimum of this distribution, they extract the value of the top, the width, top quark width about 1.9 TeV. CMS use more theoretically interesting way, and they now the total results of CMS has smaller errors about 0.36 CV. Let me remind you that standard model predicts 1.39. I skip this slide because I have no time. Also measurement some, in fact, all measurements of the TT bar production is like concerning spin properties and angle distribution more or less coincides with standard model predictions. There are also measurements of the top quark production with the Higgs, and at present, as I told you, the measurement value is more or less coincides with our expectation of the standard model. Here you can see maybe the latest Atlas results concerning the ratio of measurements, this quantity to the ratio measurement quantity to standard model prediction. As you can see, this, in fact, we have a very good agreement with standard model expectation. Let me say a few words concerning electroweak processes, a single talk. In this case, you see the total cross section is about 200 picobarons. It's about 4 times or 3 times smaller than TT bar production. We can separate 3 channels of the single top production. These differences depends on the virtuality of the intermediate W boson, and all this value was measured experimentally, and we once again obtained very nice agreement with standard model production. Here I show you the results concerning the total cross-section production, and it's the results concerning VTB measurements, and you see that our expectation from the total fit of the Kabiba-Kobayashi-Moscow matrix coincides with the experimental results. Top quark polarization, skip slide. And let me concentrate my time on the searching for the new physics beyond the standard model. There are several extensions, maybe many extensions standard model, which can produce different new ways. What we can expect if the new physics exists, we can increase or maybe increase of rare top quark decays, the deviation top quark production cross-section, production of top quark due to some unusual reaction, which could not be exist within the standard model, decay of the top quark, some unusual channels, and other. One, at present, the most effective way to analyze all experimental data is the so-called effective field theory. When we write down the total Lagrangian and introduce some new operator, in fact, we start with dimensional 6 operators, and we introduce some unknown coupling. And we measure the experimental results and obtain constraints on these anomalous couplings. In fact, historically, we start from these interactions. We have modified the usual electroweak vertices like top interaction W and B. We introduce 3 additional parameters. First, we introduce a right-handed top quark. We introduce 2 magnetic and electric and magnetic dipole moments. All these parameters was investigated carefully by focal collaboration, CDF and D0 at Fernlab, and Atlas and CMS at LHC, and the current constraints on which anomalous couplings is about within the standard model, all these values should be equal to 0. And you see here that we obtain more or less very good. What does it mean? Well, very good. For example, 0.05 from 1.2 feet, small value, but who knows? Maybe one of the most interesting study, or maybe intensive study, as the flavor change in neutral currents when top quark transit to the light quark and the radiate photon, gluon, Z boson, blah blah blah. This process could be exist. The press can exist in the standard model, but the expected branching ratio is very very small, about 10 to the minus 11 or 10 to the minus 17. Several models have predicted the extension. You can see, for example, one exotic production predicts the top decay to Higgs and charm about 10 to the minus 3, while within standard model we expect 10 to the minus 15. You see the increase could be about 10 to the 12. So there are several ways to investigate this process, and the summary are presented here. I recalculate all the quantities in the terms of the branching ratio, the upper limits of branching ratio, top decay. So let me start with the Higgs. Top decay into Higgs and up quark is less than several times 10 to the minus 4. Maybe the most another interesting prediction, top decay into glue. It's also about 10 to the minus 5. To the photon have more or less the same value magnitude. And let me show you these interesting results. When top decay, also we have flavor change on neutral currents, but with the lepton flavor violation processes. Within standard models, I don't remember, but it's extremely small value. And at present, we have very good upper limits for these results. So my colleague told me that I need to go to my finish, and let me what may be interesting. Let me spend a few seconds concerning our expectation. So now we're here. We see we have about 800 picobars with TT bar production, and there's two prediction for single top. If you consider our future, if it will be, I mean the future Hadron Collider with PP option with a square root of 10 TeV, the total cross-section will increase about 4 times of the order of magnitude. It really will be very, very nice. Let's wait. So the summary of the top quark, which I write from the RPP. Let me finish my talk with well-known slide. Thank you very much for your kind attention.
Well, Sergey, for your nice talk, and I apologize for technical problems during your talk.
Me too. I also apologize.
Please, questions to the speaker from the online audience. If there are questions from online audience, then please ask.
Oh.
Okay, I see Andrei Kataev.
Andrei Kataev. I don't see whether you see me or not from here. Hello, Sergey. I'm very glad.
Hello, Andrei. How are you?
Hello. Very glad to listen for your talk. Haven't seen you for ages. You probably haven't seen me. I don't know. The question is, to my understanding, you are not whether I'm understanding correctly that you are considering as the top quark mass, the pole quark mass, and you neglect the discussions and the minor differences of the pole quark, top quark mass from the Monte Carlo top quark mass, which is extracted and from time to time in the experimental data and acclaimed.
Ali, thank you very much for this very good question. It's, you know, it's a very long story. Moreover, you are very active participant in this story, and you perform several very interesting articles, especially you have issued the latest article this year. For my understanding, our colleagues perform measurements. These measurements are more or less coincide with each other. And this is our way, our job, our challenge to make a real interpretation of these measurements and related it with the theoretical parameters. Due to lack of the time, I especially skip all discussion concerning this very important topic. So for a moment, let me answer you as follows. I present the experimental results. Our colleagues call this quantity pole mass. Let us don't start to discuss the correctness of the term. We have at present. Now let's start to, we have three ways. First way, from my point of view, the first way, we need to improve our calculations. Second way, we can obtain more or less, well, interpretation of these parameters. And third way, maybe the most interesting, we can explain our colleagues, you have done a wrong job. Our results are senseless. But I'm not sure this third way will give us good business. So let us finish as I told you. We have numbers, and our challenge for us to make a more or less correct interpretation of this value.
Okay, so you present some numbers for the top, for the mass of the top, but you are not claiming for sure that that either this is the Monte Carlo top quark mass or pole quark mass. In fact, from this point of view, I agree with you, because to my understanding, you are doing almost all fits in the without radiative corrections.
Yeah.
In the tree level.
Yeah, exactly.
And indeed, and the differences between the Monte Carlo top quark mass and pole quark mass, in fact, they are under control and they are minor, not so essential. And when you are presenting, there are some additional theoretical uncertainties, and you present the results of systematical uncertainties for this your parameter, which you are defining from the leading order fits. Whether I understood you correctly?
Not really. In fact, when I shown the experimental result, time to time they have included theoretical uncertainties.
Yeah, okay.
Experimental result. But
they are including I agree. They are including experimental uncertainties in the systematic uncertainties.
Andrei, time to time they took into account the theoretical uncertainties. They have special values. Now we have plus minus, for example, 0.2, and in the parentheses you can see the theory. So time to time they have included, but time to time they are not.
Yeah.
So in any case, we need to investigate carefully which result we will use for our explanation.
The colleagues on the discussion until the discussion.
I will just add one moment. Every time it is necessary to read every paper,
exactly
what they are taking into account and what they are not taking into account.
Exactly.
From your presentation, it is clearly seen what you have taken into account. Thank you.
Okay, thank you. Thank you, the speaker again. Let me close the session and we meet 1 hour later. Lunch break.
Роман решали проблему. Чего? Это 10. Не на разу. Думаю, это 10. Это поможет. Было видно, он ушел раньше, предыдущий. Если видно предыдущий доклад, он и сейчас. Это выполняется как-то нет. А это настроение. Там было видно в армии, большом экране видно. На большом экране было видно. А на онлайн не было. А удаленно, да, я открыл себя, и тихо не вижу. Вижу список докладов. А вот переделали. Запомнил отсюда. Вот такая вот штука вышла. И устанавливался новый доклад, да? И он ключи знает физика. И тогда видно, и там он это все видно. То есть 3 минуты уже говорит, 3 минуты час. А у вас не правильно? Вот где-то 5 демонстрацию экрана. Это значит, что мы или нет?